Let's look at vapor pressure and boiling points for alkanes. So alkanes are non-polar molecules because they are made only of carbon-carbon bonds and carbon-hydrogen bonds, which are non-polar. And since they are non-polar molecules, the only attractive forces they can exhibit are London dispersion forces between the molecules. Now, London forces are based on the uneven distribution of electrons over the surface of a molecule, that temporary uneven distribution. And so the more electrons there are and the greater that surface area of the molecule, the stronger the London dispersion force. So if we look at two alkanes in the liquid state, pentane and octane, we see that pentane has 5 carbon atoms, octane has 8 carbon atoms, and these skeletal structures clearly illustrate that octane has more surface area, and therefore, as it has more surface area and more places for those electrons to interact and become attracted to one another, this is going to have a stronger intermolecular force. It will have a lower vapor pressure and thus a higher boiling point than pentane. When we look at the straight chain alkanes from methane up to decane, we see that as the surface area and the number of electrons increases for each molecule, the boiling point increases as well. And this is exactly what we would expect. As the attractive forces increase, so does the boiling point. Now, sometimes we have two alkanes that have the exact same number of carbons and hydrogens, so they have the same number of electrons, but their boiling points are different. For example, we have hexane, 6 carbons, 14 hydrogens, and 2,3-dimethylbutane, also 6 carbons and 14 hydrogens. However, their boiling points are different, and that's because their structures are different. Hexane is a linear alkane, and this linear alkane can easily align with another hexane molecule. The more surface area that interacts or comes in contact with one another, the more electrons that come in contact with one another, the stronger that intermolecular force. 2,3-dimethylbutane has a different structure, and we see the 2 and 3 carbon here are kind of tucked in the middle and sort of hidden from interacting or stopped from interacting with other molecules from these 4 methyl groups. So the electrons in these 2 atoms are not going to be able to interact with other atoms easily. So this has a more spherical shape, if you will, than this linear shape. And so the electrons in 2,3-dimethylbutane will not be able to come in close contact with other 2,3-dimethylbutane molecules. And your book uses this illustration here of spaghetti versus meatballs. So long strands of spaghetti, like a long linear molecule, have lots of surface area that can interact, and we know from our experience that spaghetti gets clumped together and will stay together very easily, whereas meatballs, which are round, do not have a lot of surface area that is coming in contact with another meatball. So this shape limits the amount of interaction between each meatball, and there's not a strong attractive force. So when we're looking at the London dispersion forces of alkenes, we're going to consider how many carbon atoms there are, how many hydrogen atoms there are, and then we're also going to consider the overall shape. The more linear that shape is, the more interaction that can occur. So hexane has a higher boiling point of almost 70 compared to 2,3-dimethylbutane, which has a lower boiling point of 58. That means the strong hexane has a stronger intermolecular force than the 2,3-dimethylbutane.